Hi, in this video, I'll demonstrate the solution for task 5 related to ADC converters, lab 3B. So this task is the last one in this sheet, and it's asking you to just create a simple monitoring system where the sensor, or in this case the potentiometer, is sampled periodically. And what we need to have our system do is detect whether the input voltage is within a certain range or outside that certain range. And based on that reading, based on the result of that reading, we'll be indicating different things. So we can think of this as a temperature monitoring system, for example, for a greenhouse or something like that. And where we're checking if the temperature is within a specific range, we know that the system is in a normal operation, and if it's above that, it's above the normal operation, and below it's below normal operation. And typically, you wouldn't have just LEDs in such systems. You would have some kind of a mechanism to kind of counteract these conditions that you're monitoring. Like, for example, if it's too hot, you would be above normal operation, and you could have a fan connected to it somehow so that you can turn that fan on or open a window or something like that to let the temperature drop. And if it's below, then you would have some kind of a system where you turn on a heating element or some other way of adjusting the temperature. So what we're doing here is like we are imitating a temperature sensor with a potentiometer. And pretty much that's it. We have to just be able to know what the input voltage is, and based on that, do some indication on the LEDs. Pretty simple. The difference here is that we're not going to be using the address high and low registers anymore. We're going to be using the read ADC function. So the read ADC function is given to you in the C18 reference file, and you can find out exactly what it does by reading that document. But it's just one of those functions which is available in the ADC library in the as a function. So what it will do, it will give you, when you call it, it will give you the contents of address high and low, and then you can get that result and assign it to a variable, just like what we have done here. So this variable here is declared as an integer, and we're using it to store the result of the ADC. So this only works if you have right justification. So you need to declare the ADC as a right justification to provide right justification when it's done converting. And yeah, this will return that result. So this will give you the value, an integer value of the ADC result. So you won't have to address the registers directly. And the difference between this and the previous way that we did examples was that in the previous method, we did not really save the contents of, we didn't actually save the ADC result. We actually kind of just overwrote it every time we latched, every time we converted. So by assigning it, so by sending it into a variable now, we actually have a local copy. And as long as we don't manipulate that variable, this variable will contain the current result of the ADC. So what we have here, the only thing that's, another thing that's different is these things here, these lines 15 to 17. So what I've done is, if you've watched my video about the first 3 tasks of the ADC, where I explained the hashtag define functions, this is what I've done. I've pretty much taken a note from Microchip's libraries, and I have assigned a name or a label of my choice to a pin. So in this compiler, you are able to give names to pins, because for me, it just makes it easier to remember. And if you're working in a team of software developers, for example, and you're the one that's writing the code and you have to give it to somebody else who's not particularly, doesn't particularly or necessarily know anything about the code, they can just, just glance through it and just kind of understand what's happening. So that makes your code more readable to you and to other people, because you can have this somewhere for months, flash drive somewhere, and then you open it, and if you just have a look at it and it looks like this, it can make better sense, especially if you don't have the schematic. If you don't have the schematic, having these names instead of something that makes sense would be really difficult to imagine what's actually going on. Here we have the schematic, so if we have the ports D bits instead of the label that I've chosen, it would have been just a matter of switching to the schematic and looking at what is actually connected to these pins. But this is just a neat way of doing it, and I just wanted to show it to people, so that's why I've decided to do it like this. Of course, in programming, you can solve a problem in many, many different ways. So as long as it's solved, I don't care how it is solved, as long as it's solved. So yeah, everything else pretty much the same until this point. So if you did exercise 3 and you filled in the table with the readings and you have the results, the ADC result for 2 and 4 volts, then it's just a matter of comparing the results with those values. So for 4 volts, you should be getting 818 decimal result, and for 2 volts, you should be getting 409. And then you can see that on line 32, we have an if statement, which simply takes the value of the variable result and checks to see if it's greater than 4 volts. So this is gonna this particular one is checking if we are in the above normal operation in the specification. So as you know, in the specification, it tells you if that is true, the red LED should be on, while the other one should remain off. So you can see that in all the cases, I have all 3 LEDs addressed, and this is just so that we make sure that only the correct LED is on and not anything else is indicated, because otherwise there'll be some confusion with the user, the imaginary user that we have. We need to ensure that we only turn on the correct LED. And we do this by turning that LED on and ensuring the rest are off. And that is the case for all of the cases. So in the case where this is true, this check will be skipped and this will be skipped, and we'll go back and check again. So in the case where this is false, so if the value is not above 4 volts, then we check else if. So else if only executes when this is false. So we check this. Actually, scratch that. This else if executes every time. So yes. So if this is false or if it's true, it will check this one as well. So if this is true, then it's above 4 volts and this will execute. But because we know it's larger than this will be false. So this will check this, but it will not execute because it will be false, because we know that the result is above 4, then it cannot be below 2, that's for sure. So in the case where this is false and it's not above 4 volts, then we check this and we check if it's below 2 volts. This pretty much is checking for the below normal operation, where we turn on the yellow LED. So if this is also false, so if both of these are false, that means that the value is between 2 and 4 volts. The actual result is within the range of 2 and 4. And that is when the green LED will turn on. So that's the normal operation. And I think it would be easier if we just demonstrate it instead. We're gonna put a breakpoint on these things. Keep in mind that with the simulation, the LEDs will be turning on slower than they should be because of the time of the simulation. So when we step through it, it will step in the code. It will progress the simulation with a very small amount of time, and it is not the way the voltage signals work in Proteus, they will gradually increase. I think we've already highlighted that in the labs demonstrations. So let's go and look at LAT-D as well. I think we can actually. Okay, yeah. So these are the registers that I want to show. And in this example, we have a variable called result. So we can see this will be the result of the ADC conversion. And I've just included these registers just in case, just to further illustrate. And then LAT-D, I'll just leave it in binary so that we can see which LED is actually being turned on. And yeah, so we currently have 2.5 volts. That's within the range, but let's put it above the range. And you see that when I run it, it is 2.5 and it's increasing. So what I'll do, I'll just start it over. So that it starts with that value. Yep, 4.3. Yep, okay. So we're gonna run it. Actually put a breakpoint there as well. Else if. And now it's gonna stop here. We have the result being 880. So that's above 800. That's above 4 volts, 4.2 volts. So that's our result. And now we're gonna check, is it above 818? In fact, it is, yes. So this will become true. And we're gonna go inside the scope of this statement and turn the red LED on. So you see, we're gonna turn it on, but it's not gonna actually show it. You can see the voltage change here. We have 5 volts, but it's not gonna turn on yet. So what I'll do is I'll just step through the simulation. So you see, it checked if it's below 409. It's not. So it's not gonna turn on the yellow LED. Else, that's not true. So it's gonna skip that. And then we're gonna go back. We're just gonna step through it and see this started. This is now started illuminating. I'm gonna take a few loops. And there you go. Now it's at full brightness. So above 818, we haven't changed the input, so it's still the same result. And now we're gonna try and switch it back to 50%, which is 2.5 volt. That's within the range. We're gonna keep checking, and you see as the simulation progresses, the voltage drops, and it displays green LED at 3.6. So that's correct. It will detect as soon as you're within the range. It will detect that, and it will turn the green LED on. Now we have 500. There we go. Now we have 2.5 volts at the input. We have the green LED on. So now if we go below on that range, we're gonna switch to the yellow LED. And that's how it goes. It just checks the ADC result if it's within a specific range here, and just does the LEDs accordingly. So let's disable the breakpoints, run the simulation, and you see when we get to 1.95 volts, we still have the yellow LED on. And as soon as we go into 2 volts, it's detected, then we go green LED, so we are within range. And all the way up to 4 volts, that will be the case. There you go, 3.9 is still not 4, so still the green LED. Then red, and there we go, above normal operation. So pretty straightforward, very simple. Again, there's many different ways to do this, but the if statements are the best choice, I would say. It doesn't have to be an if else. You know, it could be just 3 if statements, or it could be an if and else if structure like the one that we've given you in the solutions. So yeah, if you have any questions regarding this, drop me a message on any university system that you prefer to use. And yeah, I'll see you in the next one.